Good day, students. On this clip, we're going to be going over an example that shows how to prove an integration by parts formula using mathematical induction. Okay? All right, so let's go ahead and take a look at the formula that we're going to be proving. Basically, let's write down the question, okay? So, an example wants us to prove, use mathematical induction, mathematical induction to prove that the indefinite integral of x to the n e to the x dx equals e to the x times x to the n minus the first derivative of x to the n plus the second derivative of x to the n minus all the way down to plus -1 to the n of the nth derivative, of x to the n. Okay, so this is what we're going to have to prove using induction um, for n in the set of um, positive integers. Okay, that's the n in the set of n. All right. All right, before we start the proof, just to give you a background to help you see why this formula makes sense, and then we'll go ahead and show you why it's true using induction. If I wanted to differentiate this, instead of using the integration by parts, I can set it up using tabular integration, right? So if I put my function of differentiation on the left, namely x to the n, so I repeatedly differentiate this, and a function of integration on the right, e to the x, you notice that this pattern emerges, okay? So if I differentiate this, this is going to become the first derivative. I'm going to have d dx of x to the n. When I integrate this, is just e to the x. If I differentiate it again, I'm going to have the second derivative of x to the n, and then here it's still e to the x. And I differentiate this again, I'll have the third derivative of x to the n, and this still stays the same e to the x, okay? I'm going to keep going until this n matches with that, and in that case, we're going to have a constant, and the final derivative is, after that will be 0, all right? So if I draw my diagonals, remember this pattern continues all the way um, until I have the nth derivative. So basically, this goes on until I have um, the nth derivative of x to the n, and that will be matching up with another e to the x down there. Okay, so when I pair this up, this is a plus, minus, plus, and the pattern goes on and on. What you notice is I can always factor out an e to the x from every single term. And when I factor it out, I'm just going to be left with these derivatives going on forever. So that's why we have that there and the e to the x factored out. So that basically shows you how this came about using integration by parts. So what we're going to do is we're going to prove this, establish a rigorous proof to show that this is in fact correct. Okay, so let's go ahead and do that. All right, so let's go ahead and do the proof. Well, let me just adjust my values of n. We're going to have n be go from starting from 1, 1, 2, 3 positive integers, okay? Da, da, da. All right, so let's go ahead and do the proof. So we're going to start out with our base case, okay? So a base case for mathematical induction, we have to show that a statement is true for the first value of n. So for base case, you have to show the um, truth for n equals 1. Okay, so if I plug in 1 into this equation, do I end up with a true statement? That's the question. All right, so let's go ahead and do that. So I'm going to plug in 1 for n on the left side. So I'm going to have the integral from x to the 1 of e to the x dx. Can I express this integral as that? Okay, so basically this is the integral of x e to the x dx. I'm going to use integration by parts to show you that this is true. So using integration by parts, I'm going to set u to x, and then I'm going to set dv uh, to e to the x dx. Okay, so now I'm going to differentiate u to get du. Du is going to be simply 1 dx, and then I'm going to integrate this to get v. V is going to be simply e to the x. Okay? Alright, so the formula for integration by parts basically tells you that the integral of u dv equals uv minus the antiderivative of v du. Okay? Alright, so we have already defined our u and dv as x and e to the x. So the antiderivative of x e to the x dx, which is u dv, equals uv is x times e to the x, minus the integral of v du is the integral of v is simply e to the x, and du is dx. Okay? Alright, so this is a pretty easy integral to evaluate because e to the x is its own integral, so this is simply going to become x times e to the x minus e to the x. Okay? So can I express this integral as a variation of this formula of the right side here, namely when n equals 1? Is that possible? Well, absolutely. Well, check this out. So what's happening here is I can factor out e to the x from these two, e to the x times x minus 1. Okay? What is 1? 1 is the derivative of what? Remember, the derivative d dx of x is simply 1, right? Using the power rule, d dx of x to the 1 is 1. 1 times x to the 0, which is just 1. Okay, so I can express this as e to the x times x to the 1 minus the first derivative of x to the 1 as the integral of x to the 1 e to the x dx. And that is exactly what you get if you plug in 1 into this statement. If you plug in 1 into this statement, you have e to the x to the 1 minus 1. Okay? If you differentiate 1 further, you're going to get 0. So all these terms disappear. So you're just going to be left with exactly this. Okay? So this statement shows that n equals 1 is true. Okay? Now we have a solid foundation. Now we're ready to make our inductive hypothesis. Alright, so let's go ahead and make our inductive hypothesis. Inductive hypothesis. Alright, so what's the next is inductive hypothesis? For inductive hypothesis, we're going to assume that the statement is true for some n, namely n equals k. Okay? So we're going to assume the equation or the formula as a statement is true for n equals k. Okay? So what on earth does that mean? It means that we're assuming that the following formula I'm going to write is true. All right? How will I come up with it? All I'll do is I'll just rewrite this original equation by replacing n with k. Okay, so this n I'll replace with k, this n I'll replace with k, and this n on all the n's. Okay? So we're going to have the integral of x to the k. Notice I'm replacing my n with k of e to the x dx equals e to the x times, instead of x to the n, I'm going to have x to the k minus the first derivative d dx of x to the k plus the second derivative d squared dx squared of x to the k minus dot 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 dot, the pattern goes on, um, plus negative 1 to the k times the k derivative um, of x to the k. Okay, so what we're doing here is assuming that this statement is true. So if I'm assuming, so we're going to say assume that this statement is true for k equals 1, 2, 3, on and on and on. All right, now that we have our inductive hypothesis, we're going to make our inductive step, which is showing that, which requires us to show that if this is true by assumption, then the next step, which is k plus 1, is also true. Okay, so now we're going to make our inductive step. We're going to take one step further. Okay, so inductive step. So what are we going to show in the inductive step? So inductive step, we must show that we must show that truth for k implies truth for k plus 1. Okay? All right, so what we're going to do is we're going to try and show that if I replace this k with k plus 1, I'll end up with k plus 1 being replaced here by making use of this assumption right here. Okay? So I'm going to write the infinite integral of x to the k plus 1 e to the x dx. Okay, I want to show that this statement is also true based on the assumption that this is true. All right. So how on earth do we do that? Now what I'm going to do is I'm going to start out by using uh, the integration by parts. Okay, so as I did earlier, we're going to apply integration by parts to this formula right here. So applying integration by parts, I know that u is x to the k plus 1, and dv is e to the x. Okay, so this tells me that du is going to be k plus 1 times x to the k plus 1 minus 1, which is just simply x to the k, and v is going to be the antiderivative of this. I'm going to put a dx here. And then v is going to be the antiderivative of that, which is e to the x. Okay? Let me shift it a little bit to the right because my symbols are overlapping. So I'm going to have v equals e to the x. Okay, so I'm going to apply the integration by parts formula again. Let me write it here so we don't get confused, as the antiderivative of u dv equals uv minus the antiderivative of v du. Okay? Alright, so we already determined what u and dv are. I gotta put a dx here. So the antiderivative of u dv is the antiderivative of x to the k plus 1. dv is this whole piece put together, e to the x dx. Now note, this is the left side of my inductive step. Okay? That's what we have here. So what does that become using the integration by parts formula? It's uv, which is the product of these two. We have x to the k plus 1 times e to the x, okay, minus the integral of v du. So v is e to the x, du is k plus 1 times x to the k dx. Okay? Alright, so let's work on this side a little bit and see how we can make room to make use of our assumption, okay? So it's going to become x to the k plus 1 e to the x minus, now you notice k plus 1 is like a constant because k is some positive integer, so I can factor it out of the integration, right? So using a constant multiple rule of integration, I can factor that out. I have k plus 1 times the integral of x to the k e to the x dx. Okay? Now, what do I know about this? Does this look familiar? Well, let's go up a little bit. Check this out. The antiderivative of x to the k e to the x plus 1, you see this thing right here? This expression is exactly what I have over here. The antiderivative of x to the k e to the x dx, that's what I have here, x to the k e to the x dx. So based on my assumption, I know that this expression is equal to this whole thing right here. So I can substitute this entire expression for this integral right here. Okay? So that's going to be a little bit long, so I'm going to have to stretch it to the left. So I'm going to have, this is going to become my integral. I write it real skinny over here. X to the k plus 1 e to the x dx is going to become, just bring this side down, x to the k plus 1 e to the x minus k plus 1. Now I'm going to make a substitution. Let me change the color here so that you don't get confused about what I'm doing. I'm going to replace this integral with what I said it is equal to on my assumption. We have made an assumption that this statement is true, so I can substitute this with that with ease, okay? All right, so when I make my substitution, I'm going to end up with x to the k minus, wait a minute, I'm missing the e. There's an e to the x there. Take that out. Because let's look back what we had here. There's an e to the x outside, so I gotta put that in first. Alright, sorry about that. So we're gonna have, put it in blue so you don't get confused. We'll have, this is times e to the x times x to the k minus the first derivative of x to the k plus the second derivative of x to the k minus all the way down to plus negative 1 to the k of the kth derivative of x, the k derivative of x to the k. Okay? So there you have it. So this is basically what I get when I substitute this in the right side of this expression into my into this integration by parts component here. Okay. All right. So let's do some more algebra here to see what we can do to make this look nice. So we're gonna have, leave this alone. This will be x to the k plus 1 e to the x minus, now what I'm going to do is I'm going to distribute, you see this e to the x is already factored out. Let's leave it out. I'm going to distribute I'm going to distribute k plus 1 to everything in here. Okay, so we're going to have e to the x times, see what happens, I'm going to have k plus 1 times x to the k minus k plus 1 times the first derivative of x to the k plus k plus 1 times the second derivative of x to the k plus all the way down, I'm running out of space, all the way down to, I'm going to have k plus 1 times this term right here, which is negative 1 to the k, times the kth derivative of x to the k. All right? Okay, so now what I'm going to do, I'm going to do two things now. I'm going to factor out e to the x, which is common to both sides. I'm going to factor out this e to the x. And then I'm going to distribute this minus. Okay, I'm going to distribute the minus to every single term. And another thing I could do is I could also reorder the x to the k plus 1. You remember you can factor out constants from derivatives, so I can put it back in using the reverse of the constant rule of derivatives, okay? So actually I'm doing three things. So first thing is factor out e to the x. So if I factor out e to the x, I'm going to be left with the expression x to the k plus 1 stays by itself here because it lost this e to the k by factorization. This is also factored out, but now I'm going to distribute a minus to everything, so this becomes minus. Now I'm also going to reorder my products, okay? So I'm going to have, yeah, so this one can just be written as k plus 1 times x to the k, okay? And then this minus times this one is going to make that a plus. And I'm going to move this constant, I'm going to move it into the derivative, okay? So I'm going to have d dx, the first derivative of k plus 1 times x to the k. And then minus, this one gets distributed there too, the second derivative, d squared dx squared of k plus 1 times x to the k plus da da da. And the last term, same thing is going to happen. I'm going to move this k plus 1 in there. But note, another thing that's going to happen is when I multiply negative 1 times this power right here, if I have negative 1 times negative 1 to the k, is basically going to become, this is a 1 right here, it's going to become negative 1 to the k plus 1 using the product the product property of exponents. You add the exponents, okay? So that's the impact that this negative I'm distributing right here is going to have on this negative 1 right here. It's going to make this power increase by 1, okay? So see how I'm gonna show that. It's going to become plus plus plus, and then you have instead of negative 1 to the k, because of this distribution, I'm going to have negative 1 to the k plus 1. Okay, and then I'm going to move this constant into the derivative because you can, it's the reverse of the constant rule of derivatives. So you have d, the kth derivative of k plus 1 times x to the k. Okay? All right, it's in a lot of case today. Anyway, so now to finish this off, we're going to make use of a very basic rule, which is the power rule of derivatives. I'm going to write that in blue. What is d dx of x to the k using the power rule? It's simply k plus 1 times, I'm sorry, of x to the k plus 1. What's the derivative of x to the k plus 1? It's going to be it's going to be k plus 1 times x to the k plus 1 minus 1, which is basically k plus 1 times x to the k. Because these two ones add up to 0. So what this tells me is that anywhere I see k plus 1 times x to the k, like right here, right here, and also right here, it's going to keep repeating within all the terms, okay? So anywhere I see that, I can replace it with the derivative of x to the k plus 1. Okay, just applying the basic power rule, all right? So I'm going to apply this rule to all the x plus 1 times x to the k. Okay, so let's go ahead and make that substitution. And then it's gonna give us e to the x times x to the k plus 1 minus, this one becomes the first derivative, d dx of x to the k plus 1, okay, plus the derivative of x to the k plus 1, based on what we just said, that this expression is the derivative of x to the k plus 1, and then minus the second derivative of the derivative of x to the k plus 1 plus dot 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 minus 1 to the k plus 1 of the kth derivative of the derivative of x to the k plus 1. Okay? All right. So to finish this off, all we just have to do is multiply the derivatives where applicable, and that will be that. So it's going to become, let's put in the left side here. We're integrating x to the k plus 1, e to the x dx equals, we're going to have e to the x, that was factored out, times x to the k plus 1 minus the first derivative of x to the k plus 1. Let me put the k plus 1 in parentheses so it's obvious for you to see that we are actually done with the proof. Plus, now if you multiply this 2, you're going to have the second derivative, d squared dx squared of x to the k plus 1. All right, and then minus, if you do that here, you're going to have the third derivative, the third derivative, d third dx cubed of x to the k plus 1 plus dot 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 negative 1 to the k plus 1. And then if you multiply this, this is 1 and this is 1 right here. So using the power property of exponents, the product property of exponents, we're going to have d to the k plus 1. When you multiply the same basis, you add the exponents. This is a k plus 1 derivative of x to the k plus 1. Okay? Have k plus 1 here, you have k plus 1 here, have k plus 1 here. Bam. We're done. Okay? So we've been able to show by induction that when I replace my inductive step, you see this inductive step, when I replace all these k's, the k on the left side with k plus 1, I was able to have a k plus 1 replacement on my right side. You notice how all the k's became k plus 1 on my right side right here. So that actually shows that we're done. Okay? So since the inductive step follows that the inductive hypothesis is true, this is true, then the original statement is true. That's true. Okay? So there you have it. All right. All right. So just a quick correction. Let me just interchange my terms here. So what we just proved is that since the inductive hypothesis, the inductive hypothesis is true for n equals k. So since the inductive hypothesis follows that the inductive step is true, then the original statement is true. Okay? So the hypothesis implies that the inductive step is true, then the statement is true. Okay? So there you have it. Let me write this nicely. So this is inductive hypothesis following that the inductive step is true. Inductive hypothesis follows that the inductive step is true, the original sequence is true. So the goal again for induction is just trying to show that P sub k is true, implies that P sub k plus 1 is true. So that means that pattern will continue for any k that you select, okay? So that's the whole idea behind mathematical induction. And we've basically proven that the original statement is correct. So there you have it. So thanks so much for taking the time to watch this video. Please feel free to subscribe to my channel by clicking up here. You can help support this video by commenting or liking this video if you liked it. More videos can be found on mathgotserved.com. Thanks again and have a wonderful day.